All right. This is relationship between electric potential and electric field. Okay. Um, it's going to go by pretty quickly. Not that crazy. I'm hoping this doesn't last too long. Okay. So talking about this is kind of connecting the dots here. Talking about electric potential and electric field, how they relate to each other. Just really quickly, right? Um, if we know that from physics one, work is the change in kinetic energy. Okay. Then we know that if kinetic energy is conserved, okay, if it's conserved, which I totally just butchered right there, then we know that any increase in kinetic energy should be complemented by a decrease in potential energy. Okay, so if it's like I said, if it's conserved, then if you have an increase in kinetic energy, then you should also see the potential energy decrease. So therefore, we can say that work is equal to a negative change in potential energy, which in this case, right, we talked about electrical potential energy, it would also be negative Q delta V. Okay. Okay. Um, Another equation that we can use to relate electric field to electric potential and distance is delta V equals negative E delta X. Okay. Um, and if you rearrange that equation, you can also end up getting E equals negative delta V over delta X. Okay. So that you can see two different forms of that equation. Okay. We've talked about this, I believe, in the previous section, that electric field is the slope of V versus X. So if you have a potential versus position graph, then you would be able to take the slope of that to get electric field. And you should also know that the electric field points towards lower potential. Okay, I think we talked about this in the previous section that if it has that positive charges usually are positive potential, negative charges are negative potential. So in essence, the E field always flows from higher potential to lower potential. Okay. In order to create a spark through the air, the electric field in the air must be 3 times 10 to the 6 newtons per coulomb. Okay. Suppose that two objects are 0.03 meters away. We're just going to fill that in. It's a little bit of a dynamic question because we can change that. Okay. Suppose that it's 0.03 meters away from each other, and when a spark passes through them, between them, what must the potential difference have been between the two objects in order to create the spark? Well, if we use delta V, okay, and we know that the electric field had to have been 3 times 10 to the sixth, okay, the distance between them is 0.03 meters. You would calculate that out, and you would get 9 times 10 to the fourth volts. Okay. Okay. So this is kind of a three-dimensional example of like an equipotential kind of thing, right? We can say that this right here is like retail row. Okay. This is tilted towers. Okay. And this is Loot Lake. Okay, so if you've got those three locations, right? So let's say that this is kind of like a landscape made out of, like I guess you could say smooth concrete, right? It's not flat. There's a bunch of hills and valleys, okay? And there are, let's pretend like we have a bunch of marbles that we can start maybe at like retail row and then have it go down. And what's going to happen, right? If you take the marble here, it's going to roll down the hill and go and go, and then it's going to come up to tilted towers. It's kind of going to like half pipe a little bit, and then it's going to go just kind of throughout the landscape until it gets to the lowest point, right? That's how marbles work, right? Okay. Um, and so that's kind of an example of what that looks like. Now we can take this three-dimensional map because this is a lot to deal with. Okay, we can take this three-dimensional map and turn it into a two-dimensional map because we mostly focus on. We don't really do too much with 3D and Physics C. You can turn it into this two-dimensional map right here. Okay, this is a contour map. It corresponds to the diagram. Okay, this is like a bird's eye view of it. Okay, and you can see that there's more lines where where it's getting steeper, right? So the more lines that are there, the more steep it is, whether it's steep going up or steep going down, either way, right? Okay. In the analogy, right, the height of any point represents the electric potential. Okay. The slope at any given point is the electric field. Right? Because this is technically a potential versus position, okay? And then the marbles that we've released from retail row represent positive charges. Okay? Because positive charges are going to go from areas of high potential down to low potential, right? High potential is going to be the height of the point, okay? And the positive charges are going to follow the slope to the areas of lower potential, okay? Okay. Keep knocking my document camera. I apologize, okay? I just get so excited when we're talking about potentials, okay? Okay, the following diagrams show these sources of charge. Okay, so the top section shows sources of charge. There's a uniform density, positive Q, negative Q. These are point charges. Here's a conductor, and then here's what's called a nested conductor. You don't really need to know what a nested conductor is, okay? You just need to know that, wait, you don't really need to know what a nested conductor is right now. You just need to know that a nested conductor is where you have a shell, and then you have another conductor inside of it. Okay. Okay, and you'll notice that in the middle we have these potential lines. Okay, they they look kind of like hills and valleys, and some of them plateau. And then we want to draw arrows that represent where the electric field goes. So one way to figure out the electric field, probably the easiest way to figure out the electric field here, is actually going to be to pretend like you place a marble at the pretend like you place a marble right on the graph at that point. Where's it going to roll? Right? So if you take a look, right, if we take a look right at the beginning, you're going to notice that there is a slope that is going, down, okay? So the marble would actually travel in that direction, okay? So if we placed a marble at that point, it would go to the right. If we placed a marble at this point, it would go to the right. And you get the point, right? It's going to the right. Well, now on the other side of this little valley, this is actually going to go to the left, because if we just set a marble right there, it would go right? So it's going to go to the left. Okay, left, left. Now it's changing direction again, because now the slope is going to cause it to go to the right, 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 right. This to the left. Sorry, I should have drawn it like this. Okay. That's how I'm going to draw it, so you can see this is going to be to the right and then to the left, okay? And then right here it goes to the left and then to the left. Now, take a look at this one right here. This one is going to be placing the marble right on a plateau, which means it's not going to move at all, okay? The marble's just going to stay there. So I'm just going to circle it to show that it doesn't move, okay? Here it's not going to move either. Here it'll move to the right, to the right, to the right, to the right. This is actually a flat segment, so it's not going to move. This is going to go to the left, okay? Flat segment, to the right, not moving, because again, flat segment, okay? And then here to the left, 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 left. For the last one, you could say to the left, or you could say it doesn't move, because technically, I guess the slope kind of flattens out right there, okay? Okay, for the Van de Graaff, you would have to do this is something that you would probably do as like a demo, okay? So you would have to bug your teacher about that. But the way that you would measure it is that you would hold the grounded ball up to the Van de Graaff generator, and you would see how far away the ball needs to be to have a spark jump from the generator to the ball. Okay, and then you could use delta V equals E delta X. Okay, and E would have to be that thing that we said earlier was 3 times 10 to the 6th, I believe, newtons per coulomb, because that's the required electric field to cause a spark through the air. Delta X, you would measure it, okay? And then you would calculate delta V, okay? I'm too much of a scaredy cat, so I didn't do that with my kids, okay? We just shocked ourselves with it, and I think I died for like a second. Okay. You're going to look at this, you're going to think, wait a minute, this is mechanics, right? And yes, it is mechanics. You're not wrong about that, okay? So first and foremost, right, when you have a cart on a hill, I'm going to start with the carts on the hill, okay? Consider these carts rolling down each of the different hills shown below. On which hills does the cart have the greatest force and the greatest speed at the bottom, okay? Well, notice that each of these hills is elevated at some angle, okay? And we need to know what that angle is. We're not going to know what it is right now, okay? Because what we actually need to figure out, or we can figure it out right now actually, but really quickly, I do want to make another point, okay? I'm just going to draw it on the 3 diagram because it gives me the most space to do it. If the cart is partway on the hill, then right, you should know that it has mg going straight down, but then it has components. One component that's perpendicular to the ramp and a component that's parallel to the ramp. And I did not draw it very accurate, okay? This component that's perpendicular to the ramp, right, we would need an appropriate trig function to define, okay? Because, and also hopefully you remember that the angle right here is the same as the angle right here, okay? Which is important for us to figure out. So if that's the angle right there, then we need to figure out what's going to give us the component that's parallel to the ramp and the component that's perpendicular to the ramp, okay? So hopefully you remember that the component that's perpendicular to the ramp, in this case, we would need to use mg cosine theta. Okay, and the reason we get mg cosine theta is because this is the hypotenuse right here, and this is our adjacent angle. Okay, and then the other one we have the hypotenuse and the opposite, which would actually give us sine. So this would be mg sine theta. Okay. We don't care about mg cosine theta. We're not going to care about it, right? Because what's going to happen is it's going to equal some value. It doesn't matter, okay? It ends up getting canceled out, okay? By the normal force, okay? Now, mg sine theta is not going to get canceled out. That's actually going to be the force that causes it to go down the ramp, okay? Well, m and g is a constant. This cart's not losing any mass, okay? So theta, okay, is going to be the only thing that changes here between scenarios, right? The cart is identical in every single scenario. G is constant in every single one. The theta is the only thing that's going to change. So we have to ask ourselves, okay, well, if theta increases, okay, what happens to the whole? What happens to the whole result, right? Well, we need to figure out what theta is equal to in each of these cases, okay? We're given the opposite and the adjacent for each one. So the best way to do this is going to be using that theta is equal to inverse tangent of 10 over 10, okay? Which is inverse tangent of 1, right? That should give you 45 degrees, okay? For number 2, also inverse tangent, right? You'd use inverse tangent for all of these, okay? But you would need, okay, it's TOA, so TOA, opposite adjacent. So this would be 10 over 5, which is tangent of 1/2, which would give you about 63.4 degrees, okay? You would calculate this too, tangent -1 of 20 over 20. Wait a minute, that's just tangent, inverse tangent of 1, which is 45 degrees. We solved that earlier. And then for number 4, you would see it's also tangent, inverse tangent of 20 over 10. Wait a minute, that's half. We did that earlier too, didn't we? Okay. So the greater the theta, right, the greater the force, right? So therefore, we want to look at the ones that have the greatest theta. That's going to be number 2 and number 4. So we'd say 2 and 4 have the greatest force. Which one's going to have the greatest speed at the bottom? Well, you should know that by conservation of energy, right, U equals KE, okay? So U at the top equals the KE at the bottom. Okay, you can probably not really see that super well, okay? Well, if you know that potential energy is gravitational potential energy, right? That means that more height means more potential energy. And the ones that have the most initial height at the top is 3 and 4. Okay? So it'd be 3 and 4. Okay? So they have the most potential energy at the top, which means they're going to have the most kinetic energy at the bottom, right? Okay. Suppose a proton is placed on. Okay, so these examples correlate kind of to the mechanics ones that we just did. Suppose a proton is placed at rest on the positive plate on any of the sets of plates below. We don't need to know which one the positive is because it doesn't matter. Okay. So we've got a couple sets of plates. In which cases does the proton have the greatest force and the greatest speed upon reaching the right plate? Well, force. Okay. You know that force is equal to QE. Okay. And so if Q is constant, then if E changes, it's going to change the force, right? So we should know that E is equal to delta V over delta X, the change in potential over the change in X. The change in potential is literally, what's the difference between the potential and the two plates? We got 10 and 0. What's the difference between that? 10. 10 and 0, 10, right? 20 and 0, 20. 20 and 0, 20, okay? So we should know that delta V for each of these, this is 10 volts, delta V is 10 volts, delta V is 20 volts, and delta V is 20 volts, okay? Okay, so there's that, okay? And then we would need to plug it into our E field equation to actually get our E field. So it would be 10 volts over the distance between them, which is 10. I'm going to leave it in centimeters. I'm going to do that, okay? Because I have a degree in this, I can do that, right? And it doesn't matter because we can compare it because it's all going to be in the same units, right? 10 over 10 is going to give you 1 Newton per centimeter, okay? Or sorry, 1 volt per centimeter. It should be 1 volt per centimeter, okay? Okay, number 2 is going to give us, let's see, we've got 10 divided by 5. That's 10 divided by 5. That gives us 2 volts per centimeter. Okay, number 3 gives us 20 by 20, which is 1 volt per centimeter. Okay, and then 4 is going to be 20 over 10, which is 2 volts per centimeter. Okay. You notice this is really similar to the previous example, right? I mean, it's not that crazy. Greatest force, again, like I said, force is directly proportional to E. So the greatest ones are 2 and 4. Okay, here's 2 and 4. The greatest speed upon reaching the right plate, okay, is going to be equivalent to the potential, right? Because you know that the potential electric potential energy is Q delta V. So if you increase delta V, you increase the potential energy overall, which means you increase the kinetic energy as well. So which one has the greatest delta V? It's going to be 3 and 4. Okay. Pretty straightforward, right? Nothing too crazy. Okay. Now, one of the easiest examples, or one of the most simple ways that we represent electric fields and potentials, is by using parallel plates. Okay, we usually use parallel plates. This is kind of like capacitors, kind of, but not quite. Okay, but we have the simplest electric fields and potentials. We create them by closely spaced parallel plates. Two parallel metal plates that carry equal but opposite charges. The plate that has positive charge is at higher potential, and the plate that carries negative charge is at lower potential. So we can figure out which one has the higher and the lower potential, which direction the E field is going. Okay. Between the plates, okay, electric field's uniform. Okay, between two potentials, the electric field is uniform, so it's the same at all places between two potentials. Okay, it's the same direction. Okay, and strength. Okay, and outside, wait, and between the plates, the electric potential should be linear. Okay, that means that the electric field changes linearly throughout the plates. Okay, there's no weird stuff going on. It's not quadratic or cubic or anything. It's changing at a linear rate between the plates. Outside of the plates, okay, your electric field is going to be 0. Okay, because there's no, the electric field's literally starting on one plate and going to the other, okay? Outside the plates, the electric field is 0, and the electric potential is going to be uniform. So same strength. Okay? Okay. It's uniform, it's the same strength, right? So between the plates, right, there is a uniform electric field and a linear potential. Outside the plates, electric field 0, and electric potential is uniform outside the plates. Okay. Note, so we're going to have these examples with parallel plates. We're going to be able to show the electric potential, and we're going to have the electric potential, and we're going to have to graph the potential versus position here. You see these rulers right here? It printed like on a biology test when they show you, they're like, hey, identify this part of the cell, and it's like an arrow pointing at like a pretty much like ink blot. Like you can barely see it, right? So I'm going to do you a favor and I'm going to write what's on here. This is 4 and this is 8, okay? That's 4 and that's 8. So what's happening is we need to first figure out which plate's going to be positively charged, okay? Well, take a look at these right here. These are batteries, okay? We have the negative terminal and the positive terminal. And you'll notice that the positive terminal is linked or is connected to the right plate, which means this is going to be the positively charged plate. Okay? The negative terminals go to the other plate, which means this is going to be the negatively charged plate. Okay? Where's my red? There's red. Okay? Now, how much potential is on each of these plates? Well, if you notice, there's 2 volts and 2 volts. So the 2 volts are going to combine on the positive plate and give this a potential of 4 volts. Okay, now if you notice, the potential is going, now if you notice, right, you might think, okay, it'd be -4 going into the other one, except that there's this thing here called a ground, okay? That's a ground. Don't confuse it for a battery, it's a ground, okay? When there's a ground present, the electric charges want to go through the ground, right? They don't want to go into the plate. So this is actually going to have an electric potential of 0 volts because there's the ground there, right? So when you start graphing this, okay, it's going to look kind of weird. Outside of the plates, the potential is uniform, meaning it stays the same, okay? Well, we know that on this side of the plate, we know this plate is 0 volts, okay? So that means that everything to the left of it is also going to be 0, okay? So that means until we get to, what, 4 centimeters, it should be 0. Okay? Then, when you get in between the plates, it increases linearly to 4 at a position of 8. So at 8, it's going to increase to 4, okay? And then it's going to increase linearly, so we just draw a straight line here. If I had my ruler, I would actually make it into a straight line, but I don't have my ruler because I am in the safety of my own home. And then past the plate, it's going to be the same, okay? It'll just stay 4, okay? And the gist here is that if you had a positive charge right here, it would go this way, right? Because the E field is flowing from this plate over to that plate. Okay, you see what I'm saying? And you can also prove this because if you were to drop a marble at this position, it would roll downhill. Okay? Okay, now that you've kind of seen that example, look at the next one. This is 1 and 5. Okay, you can barely see that because of the way it printed. I keep hitting my document camera because it's right here in front of me. Okay? And you can notice that the right plate is going to be the positive one again. Okay. Now, okay. Now here's something to notice. The ground is in between the two, okay, which means that the batteries are actually not going to affect each other, okay. This is going to have a potential of -2 volts, and this is going to have a potential of +2 volts, okay. And what you'll notice, okay, is the ground, it doesn't affect, right? This is why it's not -4 and 4. It's because of the ground, right? The ground basically splits the batteries off, okay? And so what we can do is, to the left of this plate, it's going to be -2. To the right of this plate, it's going to be 2. So we know that until you get to a position of 1 centimeter, it's going to be -2. Okay? Then it increases linearly to +2 at a position of 5. So 5, +2, boom. Okay? It increases linearly, so draw a straight line there, and then to the right of this plate, it'll be 2. Okay? That's all you have to do for that. Case B, or case C, okay, we've got, this is kind of hard to see here. This is at 5 and this is at 7, okay. Notice that this time the left plate is the positive one and the right one is the negative. And again, we have that ground between our plates, or sorry, between our batteries, right? So they don't affect each other. So we should be having a potential of 4 volts here and then a negative 4 volt potential there. Okay? So starting out, we should have 4 volts all the way until we get to a position 5. Okay? Okay? And then when we get to 7, so it decreases down to -4 at 7. So it's a pretty steep decrease. Okay, that's a really big decrease. And then it remains constant, continuing out of the plates. Okay. Okay, and if we look at case D, again, left plate is going to be positive, right plate is going to be negative. Okay, and then we can see the positions of these are at, this should be 5, and this should be 8. Okay. Okay, and then you can see, the potential here on the left plate is going to be +4, and the right plate is going to be -2. Yes, they can have different potentials. Okay, that's just how the batteries work out. Okay. So then we'll graph it so to the left of this plate should be 4 until you get to 5. Okay, so right about there. Okay. And then it decreases linearly to -2 at a position of 8. Boom. Okay. And then to the right of that plate, it is uniform. Okay. All right. Pretty cool. Pretty straight up, right? Okay. Just a couple more questions to go for this one. So a proton is released from rest at the surface of the positive plate in each of the cases on the previous page. So like I said, right, we have the proton released from at rest from the surface. Rank the cases in terms of the speed of the proton upon reaching the negative plate. Explain your reasoning. Okay. Well, the reason for this, right, we kind of talked about this in the previous one, is that potential energy gets converted into kinetic energy, right? And so more potential energy, Q delta V, equals more kinetic energy, 1/2 mv squared. Mass is going to be constant, so that's not going to change, but velocity will change, okay? So more delta V equals more velocity, right? Isn't that interesting? The V's are affecting each other now, okay? So if we take a look at the examples, right, which one has the greatest delta V, okay? It looks like C has the greatest delta V because it's going from 4 to -4. Okay, delta V is 8 volts, right? It's changing 8 volts. Okay. D is going from 4 to 2. That's a change of 6 volts. Okay, this is a change of 4, and this is a change of 4 as well. So it looks like C and D are going to be first two. C is greater than D is greater than A, which is equal to B. Okay. And then finally, in terms of the acceleration, right? In terms of the acceleration of the proton between the plates. Well, if we're talking about acceleration, we should also be talking about force, right? F equals ma, okay? And for these protons, the net force is often going to just be QE, okay? Well, that means, wait, so that means more E equals more force. Okay, and how can we get E from a V versus X graph? Oh, that's right, we take the slope. So slope of v versus x is e. Okay? So we take the slope of the graphs. Okay? Well, it's pretty obvious which one has the most slope, and that's going to be c. Okay? D also has a pretty steep slope, and then you should also notice that these also have the same slope. So this is going to be, it rises what? It rises 4 and runs 4, so that's a 1-to-1 slope. This one rises 4 and runs also 4, so it's also got the same slope, okay? So the ranking would actually be the same as the previous problem. C is greater than D is greater than A, which is equal to B, okay? So it's the same thing. All right. Well, there you go. Girl, boss it up.